Welcome, everybody. I'm very happy to introduce Prabhakar Raghavan. He's one of us. He has a Berkeley PhD. And those of us who still do some theory know him originally from his book on Randomized Algorithms. From there, he went to IBM Research, and then he led Yahoo Research for many years, long time, I know quite well. And then he went to Google, where he essentially ran all of Google. I think officially it was, were there parts which were not under you at Google? I don't know. Any part of Google you know it was open. And which meant in particular, as he told me this afternoon, that he had no control over his calendar. And eventually went to people and said, look guys, we have to change that. Said, okay, what about if you're CTO? He said, okay, I'll do that. Okay, so he's now CTO of Google. He is in many societies and academies. I don't want to spend more time. I let him give his talk.
Can you hear me? At the back? Okay. Great. Thanks. So I want to share some experiences we have trying to do research using language models. And I'm going to begin with a simple warm-up story of some research we started doing, leave you with a question, then get to the substance, the central technical portion, and then spend a fair bit of time reflecting on where we are on this journey. So that's sort of the program for today. Okay. So the first little anecdote that I want to share with you has to do with load balancing in our large-scale systems. You'll see the setting in just a second. This is joint work with Amar Diwan, who's in Google Search, and Eli Apfel, who works at Brown University. Okay, so begin with a quick primer on probability, and then tell you what it has to do with load balancing, right? So if you throw n balls into n bins, then some bin is going to get a massive load, okay, to a first order about log n load. But if instead you did the following, when it's time to throw a ball, you pick 2 bins at random and always throw in the lighter loaded one, then the maximum load drops dramatically. Okay? And it gets even better if you pick 3, 4, etc. instead of 2. Okay? So that's the background probability. Now, what does this have to do with serving search queries, for instance? Right? So you have a stream of requests, and you have n serving clusters, as we call them. Okay? You don't want any request to wait too long. And so the question you have to decide as queries come in is to which serving cluster do you assign a query? Okay? That seems like a clean implementation of this balls and bins paradigm. But real life turns out to be a little more complicated. So let me tell you about some of the complications we had to study. Okay? Okay. So the first complication with if you're doing Google search is you have temporal bursts. And some of the biggest bursts happen during cricket games, as it turns out. Essentially, 2 billion people in Pakistan, India, and Bangladesh are flooding us with queries all of a sudden, especially towards the end of each game. Okay? And long ago, we used to send every query to the nearest data center, and you can see why that's a bad idea. Right? Okay. So that's one complication we wanted to study. The second one we wanted to study was actually queries come in multiple priorities. There's user queries, which must take the highest priority. There's no way you should delay them. There's a lot of system queries, like for evaluation of search algorithms, ranking algorithms, and so on, and those take a lower priority. So how do you decide the assignment and the staging of these? And finally, if you're doing this thing about picking the lightest load of multiple randomly chosen servers, you should know their current load, except you don't, right? So in fact, you have slightly stale information, and that leads to very interesting complications. All right, so you want to study this problem through both simulations and theory. And as a modern computer scientist, what do? You do what I call vibe research, okay? And my co-author Amar wrote this long and very polite prompt. This is for the most basic case, okay? But the thing I want you to note is when he gave this to the model, he was actually pretty sloppy. right? And I hate to say this of my co-author, but at the top he says power of n scheduling, but by the time he gets to the last paragraph, n turned into d, okay? And then he talks about a different n, which is further down, right? And this is not that different from the way a professor might talk to their grad student, right? They're kind of all over the map, and yet the student gets it being smart, right? And so we fed this into the model and said, show us what happens, and what comes back is something like this on the right, which says, here's how the load behaves over time. Then we could add in all these other complicating factors. In goes all of that. You get as many plots as you want. And I think of this as vibe research. I think an increasing amount of systems research is being done in this way, right? We also wanted to prove theorems. Here, the models were not that useful. Here's a theorem we proved about what happens with multiple priorities. The models, I would say, were pretty good at setting up stochastic differential equations. They would guess solutions, but they couldn't actually give you proofs. Okay? And so we said, okay, so we have some simulations, we have some theorems. What do you do then? You submit it to a conference. So we said to the model, take all of this, write a paper. And so it did. Okay, and we were ready to submit it to a conference. And then what happened? We ran into this language at the conference. It said, you shall not use language models for your research. Okay? And this is not commonplace, but there are conferences that include. Now, so we were scratching our heads. Was our use of Gemini sort of part of the methodology as deemed by the conference organization, right? And so in the end, what we decided was to redo everything by hand. So we recoded all the simulations by hand, ran them, got exactly the same results. So in this case, the model didn't lie to us. But it does beg the question, should archival forums restrict AI tools in science? And I have a perspective which you can probably figure out, but I will share it when I get back to reflecting later in the talk. I will talk about this some more. All right, so that was sort of the warm-up part, right? But really the central sort of focus that I want to have on this is the following. And as soon as I put up the slide, you'll recognize that the question I'm asking is ill-posed, okay? So I'm not asking, was AI used to solve some math problem? Because you have plenty of reports in the news media and not so news media, even in published papers, that yes, I used an LLM and it helped me accelerate my thinking and it gave me this suggestion. What I'm really interested in is the question, do these LLMs endow us with some capability that I couldn't have gotten to as a smart human with plenty of compute? Okay? And I realize this is very hard to settle beyond doubt, but I'm going to take a crack at some of our experience, show you some of the results we have, and try and argue to you that a smart human with plenty of compute couldn't have gotten them. So there is something going on, right? That's not a theorem I'm going to claim. There will be theorems you'll see in a second, but that's the direction of travel, okay? And we're going to do this in two settings. First, in the hardness of discrete optimization, which is a well-studied area for, I guess, 30 plus years. And the second is in Ramsey numbers, which is a well-studied area for 100 years now, right? This is joint work with Anshin Agda, who's a student here at Berkeley, and my colleague at DeepMind, Abhijit Takota. All right. So first, let's start with discrete optimization. And we're going to look at two problem settings. We're going to look at a problem called max cut, and then we're going to look at the traveling salesman problem. I'll dwell on the former because it's easier to explain what's going on. The traveling salesman problem is sort of grungily technical in the result we prove, so I'll just touch on it lightly and tell you what we managed to do. Okay? Now, in all of this, we'll use a tool from Google DeepMind that's called AlphaEvolve. After I get you halfway through the first result, I'll explain what AlphaEvolve did, so bear with me until then. So I tell you what AlphaEvolve is. Okay, so let's begin with max cut. So what is a max cut problem? You're given a graph on n nodes, an undirected graph. And I ask you to cut it in two pieces so that you cut as many edges as possible. Okay? It's hard to do. It's hard to even find an approximately nearly exact optimal cut. Okay? And you can consider generalizations of this problem where you want to break it into not 2, but 3, 4, 5 pieces, etc. Okay? And the first result I'm going to show you talks about breaking a graph into 4 pieces to maximize the number of edges cut. Okay? All right. So what do we actually show? Right? So we show that it is hard to approximate better than 98.7%, approximate the side of the cut. So not only is it, if the graph's biggest way of cutting into 4 pieces has 1,000 edges, even finding a cut of size 987 is going to be hard. Okay, that's what this theorem shows. Okay, and we do this using what I'll call a novel gadget reduction. For those of you who are not familiar with gadget reductions, I'll give you a quick intro in a second. Okay, all right. This beats the previous best result of 98.8%. And you're looking at that and saying, oh my God, you used all this compute at Google to beat something by 0.1%. And the answer is yes, that's what we did. This was more like we're proving something is doable. It's a 10-year-old result, so it did stand some test of time. But yes, indeed, we have a small improvement. And this is the first problem we had where we could actually beat an existing result. Okay? So to tell you how we did this, I'm going to take 2 slides to tell you what a gadget reduction is, and then tell you what we did to improve it. Okay? So here's how this works, right? I want to show you that it's hard to cut a graph into 4 pieces. I'm going to start with the problem that's known to be hard and create from it an instance of max 4 cut with the argument that if you could cut the graph well, then you could solve the original problem, which is unlikely because it's hard. Okay? So what is the original problem we start with? It's called 3 ln 4. It's a family of equations in n variables, where every equation has exactly 3 variables, and all the equations are mod 4. So everything here is 0, 1, 2, or 3. And this is known to be hard. And the claim we're going to make is, from this, we're going to construct an instance of max 4 cut, namely a graph. And if you could cut that well, you could solve this, which is unlikely. Therefore, you couldn't have done that. So that's the argument. Okay? So how does this actually work? So gadget is a recipe for taking a piece of the source problem, in this case, the family of equations, and constructing a piece of the target problem. So you pick an equation, and a gadget is a recipe that builds a piece of a graph. And then by gluing together all of these pieces, you've built a graph. And the argument will be that if you could break that graph, then you could solve these equations. Okay? I'm not going to take you through all the details, but what I want to focus on is actually what is this gadget. Okay? Okay, so AlphaEvolve, this tool that I haven't defined yet, but I will in a second, found a gadget that yielded the result. Okay, and here's what the gadget actually looks like. It takes an equation, x1 plus x2 plus x3, and builds this 19-node graph. Okay, that's a pretty big graph. And you do this for every equation. You glue together all the 19-node graphs, and you get this massive graph. And the claim is if you could have broken that, then you could have solved the original instance. Okay, so where did this come from? And in fact, these edges have weights from 1 to 1429. Why 1429? It's what the tool spat out. There's nothing I know that's interesting about 1429. It's a prime number. Other than that, I don't know. Right? But you should immediately be suspicious. Like, why do we know this thing works? How do we know it's correct? So verification is a standard hard problem in computer science, and we'll come to that in a couple of slides. Okay? So that's the program. Okay? So now I'm going to tell you what actually found this. AlphaEvolve is this tool, and here's what it does. It is maintaining a fleet of programs, in our case, Python programs. And these programs are told to go find good gadgets for this problem. Okay? And they crank away, they spit out gadgets, and you use a synthetic scoring function to tell which programs are doing well and which ones are not. You discard the ones that aren't doing well, take the ones that are proceeding well, feed them back to the language model, and out come a new family of programs. Okay? So that is the fundamental loop, right? So this is essentially an evolutionary process where the fittest programs go back and create fitter programs. And you're all the time studying the gadgets to see if they, right? And this ran for, in our first run, like a week. Since then, we've got better at this, to spit out that gadget that I just showed you. Okay? And then we could take that gadget, verify it in a way I'm about to show you, and there's something interesting going on in the verification, and say we therefore conclude that it is NP hard to solve max 4 cut better than 98.7%. Okay? Okay. So one way to think about it is somebody way back, wrote a proof that max 4 cut, you could take the 10-year-old result that I talked about, has a gadget reduction that shows the 98.8%. And what we did was to essentially snip out that gadget that they had and plug in the new gadget. Those of you who like to think about gene editing can think of this as a form of that, where you snipped out that little piece, plug this in, and then you make the claim. Okay? In general, the way you'd verify that a gadget is working is to try every possible way of breaking this graph into 4 pieces, right? Which is a humongous number of things to try, and even just at the scale of 19 nodes in the gadget, right? This is a very slow process. So what we resorted to was we went back to AlphaEvolve and said, can you speed up the verification? And what follows is kind of interesting, okay? So I'm going to tell you about that now. Before I do that, I just want to reiterate 2 things. Number 1, the hardness is not for 19 nodes, it's for all n, right? But also AlphaEvolve, remember, has some synthetic objective function. It doesn't know it's actually trying to prove a theorem about cutting graphs into 4 pieces. And so it is acting completely, in some sense, syntactically, and still generating these graphs. All right. So now let's get to the verification, which I think is one of the things that we did that was instructive. Okay? So we're trying to find a verifier for breaking graphs into 4 pieces. So we made it generate a lot of max 4-cut instances, okay, with varying amounts of edge density and so on. And we said, what's the biggest gadget you can verify within 1 second? Okay, and why 1 second? It's a system constant we just chose, because exhaustive verification would take like a long time, right? And we did that, and AlphaEvolve comes back and says, here's a verifier. Now, how do you know that verifier is correct? Well, we don't actually, but what we did was we took this synthetic verifier that AlphaEvolve spits out, checked it on this data set, passed the checks. We used the language model to critique the verifier, and finally ended up with a verifier that satisfied this property that in 1 second, it could say, yep, this is a good gadget, or not. Okay? Now, if you ask me, do you know for sure that this synthetic verifier was good? The answer is no, but it's fast. So it's fast and sloppy, and when you're putting this in the inner loop of AlphaEvolve, which is going thousands and thousands of times around, it works. However, before we asserted the theorem, we actually did a brute force verification. So you spend a lot of time at the very end before you write a paper saying, okay, this verifier actually sound. Well, the verifier isn't sound, the gadget is sound. Okay? I still don't know if the verifier is sound. Okay? And this is one of our takeaways, which we use consistently in all the results I'm going to show you. Fast and sloppy verification can lead you to a result quickly, which you then take a lot of time to verify. Okay? And just to give you a flavor of the kind of thing, for the max 4 cut, it devised a branch and bound strategy, and then it did some funky Python library things that I don't even understand, and came back and said, this works. Okay? So this is just to give you a sense of how in the process of doing this work, of proving the theorems, we had to go through these shortcuts, but then we did the long version of it at the end. Okay? Let me briefly touch on a couple of more results, right? So the max cut, I said, for breaking it into 4 pieces, in the worst case, 98%, right? This is an imprecisely stated results, but if you take a random graph where every node has 4 neighbors, it's unlikely, and I'm not going to qualify exactly what's buried mathematically in that unlikely statement, that you can verify its cut to within 5% of optimal. This builds on some earlier work of Kuniski and Yu, and it follows the same template. We took their proof, and in the proof, there was a small Ramanujan graph that they had, and we used AlphaEvolve to build a big Ramanujan graph, and that gave us a better result. Okay, and in this case, the result is essentially the best possible we could show, and therefore, this is sort of closing off an area. Okay? But the schema is essentially the same. You take a proof. We don't bother to try and change the whole thing and verify the whole thing. We take a snippet of it, improve that snippet, and make the claim. Okay? And the rest of it, we leave intact. So all we have to do in some sense is verify the interface between the gadget, or in this case, the Ramanujan graph, and the rest of the proof. Okay, I'm going to take 2 minutes to tell you about the traveling salesman, the result. It's very similar in flavor. Okay, so what do we have? We have the metric traveling salesman problem. A salesman has to visit n cities, traveling the shortest total distance. We assume the triangle inequality, so it's a metric space. And the best known upper bound is an approximation algorithm that slightly beats 50% over optimal. Okay, this is due to Carl and al. And this beats like a 50-year-old result where it was exactly 3 halves, and they're like better than that by 10 to the minus 30 or something like that. Okay. On the other side, there's a paper due to Klebik and Klebikova from about 10 years ago, which finally got published in 2020, that said getting closer to optimal than 117 over 116 is hard. In other words, if the optimal tour is of length 116, even finding 117 length tour is hard. Okay? Now, we improved that to 111 over 110, and I know that half of you are squinting saying, is that actually an improvement? It is, right? So in this case, this new result very slightly beats the old result. Okay? And again, I can understand your reaction if you say, okay, did you work this hard to get that minuscule improvement? And this is a problem that's been studied for some 30 years. So even this, an improvement in this comes along once in a decade. So even this is good progress. It's a reduction from a problem called hybrid 3-2. I'm not going to get into that detail. But it's something we felt good about. It's a classic problem, and this is now the state of the art. And again, the schema is the same. Well, actually, we had to do a little more work here. So there was a series of existing papers. We had to take them and rewrite the proofs in a way that a clean gadget reduction emerged, okay, so that it actually follows this picture. And then it was a matter of replacing the gadget by a better gadget that AlphaEvolve found. Okay? Good. Let me now get to the next family of results where we used AlphaEvolve. Okay? And this is the setting of Ramsey numbers. So for those of you who don't remember Ramsey numbers, let me give you sort of the 30-second version, right? So Ramsey's original observation is if you invite 6 people to dinner, then inevitably either you'll have 3 mutual friends or 3 mutual strangers. In other words, if you 2-color the edges of case 6, then either you'll have a red triangle or a blue triangle. But it's not true if you have only 5 people, right? Because if you look at the picture on the right extreme, you can arrange the friendships in strangeness so that there's no red triangle or blue triangle, right? So the classic question is, given 2 integers r and s, right? Let's say r33 is 6 to denote the thing in the middle, right? So in general, you're asking what is r of r comma s, okay? So I'm going to show you what AlphaEvolve found and give you a glimpse into the kind of things it did along the way, okay? So first, the results. Okay. So in general, how do you find these Ramsey numbers? We don't know how to. But if, for instance, I could find a graph with 36 nodes in which a coloring of 36-node graph without any 4 friends or 6 strangers, you know that R46 is at least 37. So this is a lower bounding technique. Okay. And using this observation in general, here's all the lower bounds that AlphaEvolve has found. So let me walk you through this in what it's saying. Okay? So the rows and columns are R and S. A blue cell is a case where we found a lower bound that matches the best upper bound. In other words, it's a tight bound. None of these is a new result. They've all been found previously. A yellow cell is a repetition of a previously known result, meaning somebody else had found it and we matched it. A green cell is new results, meaning these are new results that nobody had before. They break the world record. This table is actually about a week old, and there have been more cells that have been filled in the interim, so we're continuing to fill cells. Okay? So there's a few things I want to share on what it took to do this, right? First, we looked at the code that was being generated to fill each of those cells. And I cannot give you a pattern that says, well, if the code for cell number 3, 10 looks like this, then here's how we would construct the code for 311. It's like each was bespoke in some ways, right? This is not to say there is no uniform approach somebody else can find. It's like our code generated by AlphaEvolve is different for each cell. And this is not the raw code. This is, we took the code, fed it to Gemini, and these are the summaries that Gemini generated for each code. So for instance, on the left, for 311, the cell 311, it said, well, start with a diverse pool of algebraic graphs, cyclic graphs, blah, 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 right? And then it gets into some jargon, but it actually talks about how the algorithm worked. But the code for 313 looks completely different. Okay, so my point here is it's as if you hired a grad student or 10 or 20 or 50, had them chase a cell, use all your information and knowledge of Ramsey theory, and just focus on the one cell. And then the next team of grad students did something completely different. Okay? And this has sort of been a hallmark. So on that table, you saw about 30 numbers, and all 30 look kind of different. There's not a whole lot of, right? So each cell has varying difficulty. Some of them we cracked quickly, like in a day. Some of them took more, right? I cannot give you a simple unification of these various algorithms, but the meta algorithm is AlphaEvolve that is printing out or evolving these different algorithms. Okay?
Excuse me, but by evolving, do you just mean optimization?
Well, so by evolving, I mean this loop of taking successful programs that are making progress towards a good Ramsey number, feeding them back, and spitting out. So it is, in some sense, spitting out more optimal programs, but it's not optimization in the standard sense of math programming. Right? If you look back at the literature, in some sense, it took many successful approaches that had been previously used and chained them together in bizarre ways to come up, not in any way we could explain. Right? We published all these algorithms, and in fact, several of the previous records were held by a somewhat large and mysterious Russian project that published the graphs showing the lower bounds, but not the algorithms that found those graphs. And we now have reconstructed those, we've constructed algorithms that give those results, not necessarily the same algorithms or graphs. Okay? Again, you can use fast and sloppy click counting along the way to speed up this process. Okay? All right. So I'm going to spend the last 10 or 15 minutes reflecting on where we are. And I hope you'll see that I've been careful not to claim anything about LLMs thinking and reasoning and being brilliant at these results, because I don't know of any such thing to hold. Right? But I will try to convince you that it would be hard for humans to have done what these do. Right? And you don't have to believe me, but that's going to be the line of argument here. So, all right. So first, how proud am I of these particular results? Well, as original research results, they're not perhaps the ones that I'm the proudest of. But to me, the significance is not exactly did we improve 0.1% or Ramsey lower bound by 3 or 4, but really how we got there, right? So first, the current use of AlphaEvolve is, as I said, syntactic. It doesn't really know it's doing Ramsey theory or complexity theory or whatever. So conceivably, and this is one of the directions we're exploring now, conceivably better models that are better equipped with problem semantics, like you are working on Ramsey theory, therefore consult everything that has to be done, that's been done in Ramsey theory, should lead to better results so that AlphaEvolve knows what it's looking for and adapts. Right? The next point I want to make is that proof verification in all these cases is hard, but the use of fast and sloppy verifiers within the evolution loop is a very powerful technique, provided at the end of the day you have the means and the wherewithal to do an exact verification, whether it's through trying all combinations of Boolean variables, which we did, or you can write a lean prover or whatever it is that you want, right? So in that sense, one of our insights here, I think, is as you're building up a proof, you don't have to be like super exact. You can actually make progress without it. Right. Could a talented human have produced these results? And we spent a lot of time debating this, right? And when you look at a gadget on 19 nodes with edge weights from 1 to 1429, I would submit that it's difficult for a human with a paper and pencil to come up with that, right? This is not a definitive argument. I'll also add that when humans try to handle large objects and of this sort, they look for symmetries to speed up how they think about it. And the TSP proof, the gadget we found, is actually asymmetric. I should have pointed this out, but the gadget is somewhat asymmetric and not the first thing that you as a human might think of. Okay? Obviously, it's difficult for me to argue that no human could have matched our AI-assisted proofs. And in fact, it's entirely possible some of these results will be improved by a human giving a much simpler proof than we have, right? Just the fact that we found a large gadget doesn't mean that everybody has to find a larger gadget, right? On the one result I showed on the average case hardness of max cut, it did need a larger graph, and we've sort of hit the limit. So I don't expect humans to improve that, right? So ultimately, I think what will judge us is the test of time, because you do see a lot of reports of AI-assisted proofs quickly get superseded by humans saying, yeah, I did that. I went off to think about it for a day, and I found the same thing, right? And conversely, people do say, well, I could have done this in a day. I think Timothy Gowers had a tweet that said, something that would have taken me a week, the LLM helped me do in a couple of days. But that, to me, is not, in some sense, superhuman capability, right? So I want to submit that AlphaEvolve, in the incarnation of generating programs that generated pieces of proofs, it has, in these cases, done something interesting. It's broken the state of the art, and the test of time will decide if that remains the best possible. Right. Now, could comparable computing have succeeded without AI? And again, it's difficult to give you a definitive answer. What I can tell you is that for the kinds of proofs we were looking at, we tried a bunch of alternative formulations through SAT solvers and through math programming methods, and we couldn't come close to these because the scales just exploded on us. Okay? Now, you could counter that by saying that's because you're not very smart the way you do math programming or whatever. In fact, the earliest advances of this type were due to a piece of work that used linear programming, and I'll come to that in a second. Right? There's this interesting note recently put out by Elkanan Mossel, who says, look, if you're going to claim that something was done with AI, you should have a criterion for being able to refute that claim. Otherwise, it's not fair. And moreover, if you're going to claim something was done with AI, it should be a fully replicable experiment, right? And in that sense, we're still work in progress. There's a lot of work out there saying I prompted interactively for a week and got somewhere. And Mossel makes this point that unless you're replicating every prompt and showing people what you've done, it's a little difficult to describe that as a scientific experiment. And I think that's a good argument. Right? I did mention that some of the early work on this, of this style on proving hardness of approximation results use linear programming. And this is almost 30 years old now by Trevisan et al. So we were inspired by them. It's just that we thought that math programming had hit its limits, and which is why we reached out to AlphaEvolve. Okay. So we've struggled to understand what AlphaEvolve is doing in the innards. The one thing, it does seem like using the model to evolve code to print out proof fragments seems more powerful than asking the model to print out proof fragments. We did actually, and I'll say a little bit more on this in a second, right? But the feeling we had repeatedly is you have a fleet of research assistants, maybe thousands, to try various approach, and especially this was evident in the Ramsey search that we have, right? But we don't yet have an understanding of why it wins, or even whether this kind of interaction, where an LLM prints out programs that print out gadgets or Ramsey graphs, is really the most optimized one. In fact, we are trying to build a system that does better. And I know that Berkeley is one of the places that was participant in this program called EvoX, that is an improvement, I believe, on AlphaEvolve, that has some nice new ideas, and I think that has some legs ahead. So people often ask, why don't you just prompt the LLM to find the gadgets or the Ramsey graphs? And this was a dismal failure, I'll say. We couldn't come close, right? On the first anecdote I gave you, even with straightforward stochastic differential equations, the state-of-the-art models struggled. And unless you do the hard math yourself, it's hard to claim a theorem. Okay. For the latter two pieces of work I talked about, hardness approximation, Ramsey, we tried hard and got nowhere. We made no progress at all. And in fact, in some cases, we couldn't reconstruct the state of the art, even though that should have been in the model training. Okay. I'm often asked, okay, how much computing did you use? And surely you guys are experts, and that's why you were able to do this. And these are valid questions. I think we're early enough in the journey that I'm not sure they're the right questions. We're asking whether it's barely feasible. The answer to the question, how much computing, we used lots. And it came to the point where I've said to the team, look, we should stop burning cycles, because we're burning cycles out of ignorance, and we learned a lot, and so we're getting a little more sophisticated. I dare say some of the earliest results we got, we could probably speed up by a factor of 100 soon. That's because we made so many mistakes. So there will come a time to calibrate, okay, how much compute did you burn to get a theorem? I don't think we're there yet. Right? In terms of how much expertise, I hadn't thought about Ramsey numbers very much until a few months ago, and I'm not an expert on hardness of approximation. One of my co-authors may be, but I don't think it was just our expertise powering these results. We're actually getting some mileage from this. So it remains to be seen over time exactly what we're getting. Right? Now, there's other ways, stepping back a bit. Many of you have seen AI help math CS research. So you can say, hey, I'm an expert in algebra, and I want to get familiar with Ramsey theory. And the LLM will write a beautiful 60-page summary of the state of the art, 10-page if you want, whatever, and give you a pretty good idea of the state of the art in this field. Right? When we tried, right, we often got useful summaries, but also a lot of nonsense. We've constantly lectured about models would tell us to use quantum entanglement to do something or the other, and I don't know how to use quantum entanglement, right? But I do think this avenue is going to be useful over time, because a non-expert can quickly approach a field, and this will lead to more cross-fertilization across disciplines. And I think this is a very powerful thing. Right? You can get suggestions on attacking a problem. It was like, why didn't you try this? We did not get useful cues, right? And I would venture that the results we have are beyond such direct LLM use, where like you suggest an approach and let's go back and forth a bit, right? Obviously, I'm not able to give you proof of that. Okay? Now, out there in the social media and the popular media, you see lots of claims of, well, I solved this open problem using AI, right? And one of the things I've noticed is that you see this less with problems that have been around and studied heavily to attack using direct LLM prompting. And even within our use of AlphaEvolve, some cells fell faster than others, including things where you might say, okay, that's a more obscure cell, so maybe people didn't pay much attention to it. So it doesn't seem to have strictly to do with some notion of how much attention it got. There's something else. Especially with the small Ramsey numbers, I actually think it has to do with the modular characteristics of the two integers being studied. I began with a quote from Dottore, and one of the things he said, this was like almost 25 years ago, is computers are going to be a powerful ally, but they're never going to replace human mathematicians. And that led me to wonder, what is it that we think of as human mathematicians doing? And there's this very nice essay by Bill Thurston from about 30 years ago that some of you may have seen, right? And in this essay, he says, the question is not even how do mathematicians make progress in mathematics. Rather, he says, I prefer how do mathematicians advance human understanding of mathematics, right? And so let's say, I began thinking about this, and if someone comes to you and says, I have a 1 billion-line lean code proof of Fermat's last theorem, have they advanced mathematics in any way, right? I went to Gemini, of course, and said, okay, what's a good way to think about conceptually Wiles's proof of Fermat's last theorem? And it came back with this, right? And it actually, personally, I found this much more useful than a 1 billion-line proof, because it does make the connection between algebraic geometry, starting with Weil, Taniyama, Shimura, all the way to through Frey curves, right? And so, to me, it seems like merely having a proof, including that 19-node graph, doesn't necessarily improve your understanding. It's somehow a record that has been held, right? Okay. One of the things that become very conscious of in this is models, AI models, get trained on success stories, including proofs that people published. The failures don't go into they remain in our heads. And in this sense, human mathematicians encapsulate a form of knowledge that doesn't get into models. And when we do, as professionals, try to prove theorems, our past failures actually influence where we go. And that doesn't get reflected anywhere in these user models. So let me go back to a question that I asked early on, right? So should LLMs be banned from science, right? So I would claim that we have at least one Nobel Prize that wouldn't have happened without the use of RL, actually, not LLMs, right? And so the genie is out of the bottle bound, whatever, right? And banning models from science is a bit like banning microscopes from biology or telescopes from astronomy or whatever. And I was discussing this with a very senior computer scientist, and he said, well, but how do you know that the results are right? And you put your name on the author list, you're taking responsibility for it. But I think he had a good point, which was we will get besieged by a flood of false, bad results, and who's to mind the ship, right? And in fact, there's a sample from a couple of months ago that shows that about 20% of new CS papers show some marker of LLM-assisted writing. That's assisted writing, that may be fixing your grammar, whatever, but nevertheless, right? The language that recurs in those papers has a sort of a repetitive flavor rather than trying to explain concepts. Going back to the point of the mathematician's job is to make mathematics more understood, right? So some of you may be aware that Archive Online has implemented a new policy because there was a flood of people writing review papers with LLMs, which served as a cheap way of boosting H indexes for people, right? So in computer science, this is the new policy because you had these AI-generated surveys. Good. So just to sum up, right, LLMs are becoming complex for vibe research, lots of potential for low-quality surveys. We are not at a point, I believe, where there's some definitive capability that AI has provided. When Move 37 happened, the second game between AlphaGo and Lee Sedol, there was this notion that experts came together and said, well, we really think that's not something humans would have done, right? So I mentioned sloppy verification, right? My best model is right now, AlphaEvolve is akin to having a large number of pretty smart research assistants, and surely seems more powerful than direct prompting. Right? I don't think I can claim to have deepened human understanding, even though you can use models to provide literature surveys and so on and start the process, but not actually arrive at theorems. And so I feel like this is a landscape that's changing so fast with so much to do. I found this beautiful line in Alan Turing's paper on where he talks about the imitation game. Right? And he talks about all the forms of learning, supervised learning, et cetera, that are ahead. But then he concludes with this wonderful line that says, we can only see a short distance ahead, but we can see plenty that needs to be done. And that's kind of where I feel we are. Thank you.